Hello and welcome to this lecture where we'll look into some of the most fundamental and important problems of physics and cosmology. The first part we will look into is what is known as a standard model, the collection of all the elementary particles. And we will ask questions like, is it really correct in its current form, or do we need to change our approach to physics in order to understand what matter is truly made of? We will look into that later on here, and let's see if we can solve those problems. Before we move into the standard model, I want to show you a little bit of history about how science has changed the last 1.5 century. If we go back to the 19th century, we only had two different kind of fields, the gravitational field and the electromagnetic field, which Maxwell defined in 1864. When Einstein introduced special relativity 40 years later, it became even clearer how electromagnetism is just two different aspects of the same. And it was very clear at the time that all physics was built on just two different fields, and no other fields were existing. 10 years later, Einstein introduced general relativity, and the last 30 years of his life he worked very hard to unify those two fields. This was in his attention almost every day until the day he died in 1955. What have happened since then is not only that nobody has succeeded to unify those two fields, but we have rather introduced continuously new fields through the discovery of new elementary particles, which according to our theories are excitations into respective fields. We need 18 different fields today. So the big question then is, where are we heading for, and can we still get back on the same track that Einstein was on? And yes, I think we can, and this is where I'm going to show you some techniques we can use to better understand how we can do so. You may be familiar with the periodic table and might think that it's not that strange that we need 18 different fields to make up that big diversity of elements, but that's not the case. All the elements in the periodic table are made of just 3 different elementary particles and the forces between them. These are the electrons and 2 different quarks. The electron is the outer shell of the atoms, and the nucleus is made of protons and neutrons, which again are made of quarks. A neutron is made of 2 down quarks that become equalized by 1 up quark. That's how it becomes neutral, and that's why it's called a neutron. For protons it's the other way around, so they are equal to the electrons, and that's why the number of electrons and protons is always the same for neutral atoms. And this is it, all atoms are made of only those 3 elementary particles and the forces between them. The entire periodic table is just a product of how the number of those 3 can make many different categories of properties, and they are what we call the first generation of particles. The next 2 columns are the second and the third generation of particles. They have identical charge to the first generation, but are short-lived and more massive particles. At the bottom we have the neutrinos, which are chargeless particles. And these are the 12 normal particles. To the right we have the antiparticles, which are identical to the normal particles, just with opposite charge. We then have 24 particles in total, as well as the force carriers, also known as bosons. Photons are responsible for electromagnetism, gluons for the strong nuclear force, and ZW bosons for the weak nuclear force. These are the 3 fundamental forces we have beside gravity. So the big question here is, how can they all be fundamental? Which leads to the question, what is an elementary particle actually, and what is a charge actually? And I think these are both the same question. An elementary particle is a charge with a mass, and that's what we know. We always hear people talking about electrical charges like it is some kind of a well-known phenomenon, but the truth is that we don't know what an electrical charge is at the fundamental level. What we know is that everything is situated in a field and have wave-like behavior, but all the numbers are just something we identify through measurements and calculations. For example, we measure the mass of a quark and then we implement the numbers to the model. What a particle in itself is, that is something both philosophers and physicists have struggled to answer for not only decades but also centuries, and we still don't have a clue. And it's the same case for all our science so far. It is built on constants. Our historical scientists have done a formidable effort to figure out how those constants hang together and can be formalized as physical laws, but we still don't know why they are what they are. Hopefully we will find some new answers in the future, but first we need to solve all the problems with the model. So let us start with some techniques to illuminate them. The first thing I'm going to do here is that I'm going to move the electrons up to the top of the model so we get the charges by ascending order. We have the zero level with the neutrinos, 1/3 down quark section, 2/3 up quark section, and 3/3 the electrons. And this is it. It's not complicated or hard to understand. We only have those 3 charge levels. They are fraction in 3 and they perfectly coincide that way. The next thing we can do is that we can remove all the names. And names are not important. What is important is the numbers, which is the physical identity of the different particles. And as we can see here, we only have 2 different kind of numbers, which is the charges and the masses. Don't worry about the quantum spin, this is the same for all. At the end, before we move into the problems, this is the main technique we will use in order to eliminate them. We will go 3D and move the antiparticles into the backside of the normal particles. So we have the normal particles at the front end and the antiparticles backside. We will come back to the importance of this technique as we introduce the solutions eventually. We can also see the same thing for the classical model setup. We just split the antiparticles away and move them backside. The first big question that you might already have noticed is why the charges coincide perfectly with 1/3, 2/3 and 3/3. This may not sound as a problem, but in my view it definitely is. No constants can coincide that way without an underlying reason for why they do so, and all other problems should be considered in view of that. What makes this even stranger is the mass-charge relation. The up quark is about 4 times as heavy as the electron, and the down quark is about 9 times as heavy. Intuitively, it should be the other way around. It's important to have in mind that mass is a measure of energy. Then we can ask, how can we make something more charged with less energy? And yeah, it's the same problem for all the generations as well. The next problem is the color charge. Why are quarks color charged while the electrons are not color charged? The color charge is what makes the strong nuclear force, and it is considered to be distinct from electrical charge and the electromagnetism. But is this actually true? Well, we don't know. All we know is that no theory so far has succeeded to unify them. The strong nuclear force does also have a very limited range, about 2 femtometers, and this range limit is also why this is the diameter of the nucleus of atoms. This may not sound as a problem, but in my view it definitely is a very big problem, because the strong nuclear force is about 100 times stronger than the electromagnetism, and the range of electromagnetism is considered to be infinite. Even galactic structures exchange the magnetic forces, and there is no explanation for why the strong nuclear force as a fundamental force should be limited in range. We only know that it is. And this is also something we can see in view of the properties of photons and gluons. Photons are the carrier of electromagnetism and gluons of the strong nuclear force. Except that gluons have the limited range and are only present in bound states in the nucleus of atoms. They have identical properties to the photons, so why do they share properties? Are there any relation between them? There is also a problem with the strong nuclear force called the strong CP problem. I don't going to take the full story of that here today because that requires some background knowledge to hang on, but the short story is that the color charges show behavior like electrical charges without an explanation for why they do so. I think all those problems with the strong nuclear force are related, so a good theory should solve them all in one. The next unanswered question is why different particles have different lifetimes, also known as the decay time. The second generation is short-lived and the third generation even shorter-lived. And there are also big differences across the charge levels. Among the biggest problems of all problems is the matter-antimatter asymmetry problem. When we have pure energy, like the primordial universe before Big Bang, we can only make matter through pair production of particles. This means that energy can only be converted into identical numbers of normal particles and antiparticles. And when they exist in identical numbers, they will also annihilate and disappear accordingly, and no particles will be remaining, so no universe in the form we know of can exist within these conditions. And this is what is known as the matter-antimatter asymmetry problem. Why didn't the particles annihilate and disappear in accordance with the theories? And since they don't, where did the corresponding antiparticles end up? We don't know, and we should know, because our theories are not complete before we do so. One of the last problems, which is more debated whether it is a problem or not, is the physical existence of the quantum fields. According to the current standard model, all particles are excitations in the respective fields. An electron in the electron field, a photon in the photon field, an up quark in the up quark field, a gluon in the gluon field, and so on. In my view, this is definitely a problem, and I share this viewpoint with, among other, Einstein. In his Nobel lecture, Einstein said, "The intellect seeking after an integrated theory cannot rest content with the assumption that there exist two distinct fields, totally independent by each other by their nature." And this is exactly what we have today. Some fields are not independent, but many of them are independent, and we have many more fields than the two that Einstein wanted to unify, which I think he would dislike it very much if he were alive today. So then we can ask, should we listen to Einstein or not? I think that we definitely should listen to him. Although it's almost a century since his heydays, his arguments are strong, and in my view, no physicists today have strong counter-arguments. There is only a lack of knowledge about how it all hangs together. The very last problem I will mention is the charge opposition inequality. For electrical charges, we only have two oppositions, plus and minus, also called positively charged and negatively charged. All normal particles have a corresponding antiparticle. For the strong nuclear force, on the other hand, we have three oppositions theorized by the use of colors: blue, green and red. That's why it's called the color charge. So the question is simple: how can two fundamental forces have different numbers of oppositions? This is where I want to go 3D. And then it becomes much easier to visualize this inequality, and we can continue with asking, do we really know that there is an inequality? It is a matter of fact that antiparticles in general are hard to identify. We can only detect them indirectly. If a third opposition of electrical charge were existing, would we be able to detect it? Before we look into that, I want to show you how this could impact the other problems we have on the table. If we go back to when protons and neutrons first were detected, they were just as quarks considered to be elementary, until we figured out that they were made of quarks that equalize each other. Like the neutron becomes neutral. Then we can ask, can the quarks themselves be made the same way by even smaller particles? And can they be made by electrons? Well, an electron and its opposition, the positron, can only zero each other out, so with only two oppositions, this is not possible. If we introduce the third opposition, on the other hand, we can take three oppositions and add them together, just like the quarks themselves are confined within protons and neutrons. And since they vibrate three-dimensionally with three phases each, they equalizes to 1/3. If we add another one, it equalizes to 2/3, which coincide with the charge of the up quark. And not only does it coincide with the charge, it also corresponds well to its mass. In this way, it can explain both why more mass can make the charge smaller and why the charge coincides with 2/3 in the same time. If we then take three bunches of those oppositions, it is again equalized to 1/3, which coincide with the charge of the down quark, and simultaneously it also corresponds well to its mass of 9 electrons. And then we can say, voila, we have unified the atomic structure into one single charge. And it will be the same thing for charm quarks made of 4 muons, strange quarks made of 9 muons, top quarks made of 4 tau particles, and bottom quarks made of 9 tau particles. We can see the same thing in the classical setup, the entire up quark section made of 4 and down quark section made of 9, so we simply unified the quarks with the electrons. Then we can ask, why do all the particles exist in 3 generations with similar differences in decay time? If the theory is correct, it can only be answered as an underlying relation between them, and since the charge is identical, it is likely the same particle, just in another state. Then we have unified all the particles into just one particle and its antiparticle, the positron. And the way we do this is by introducing the third opposition. Let us call it the triatron. On the front end we have the electron and the positron and triatron on its backside. Then we come into the next problem on the table, and we can ask again, why are quarks color charged while the electron is not? Well, an electron does not contain any equalized charges, so as we move a quark towards it, there is no additional force added. When we move the quark towards another quark, on the other hand, the charges that lies equalized within them starts to interact when they come close enough. And then we get the strong nuclear force, which has a range of 2 femtometers. Thereby the range limit can be explained and is not anymore a problem. In view of that, we can move forward to the photon-gluon similarity. Why do they share properties? Well, it's because they are the same thing, just that gluons are the interaction between equalized charges. Maybe we should rather call them photons in bound states. Well, that doesn't matter, but anyway, we can unify the two forces into one. And this also supports what Einstein said, that totally independent fields without interaction cannot exist. The quarks do not interact with a distinct stronger fundamental force. Those charges lies equalized within them, and that's why they work that way. And then we have the strong CP problem, which is not anymore a problem, because if the color charges are made of equalized electrical charges, that explains why they behave that way and follow CP, which stands for charge parity. In view of the equalized charges, we can also theorize the decay time differences. For example, a strange quark has a lifetime that is about 10,000 times as long as the charm quark, which is likely because it contains more equalized charges that takes longer time to annihilate. The same thing is the case for top and bottom quarks, where the difference is even larger. And this is also the same thing we see for quark-antiquark pairs, known as mesons, that live much longer than electron-positron pairs. Then we come back into the matter-antimatter asymmetry problem, which, like the strong CP problem, is not anymore a problem, because an asymmetry must exist when we have 3 oppositions. However, although we have 3 possible oppositions, the particles will still be produced through pair production, so they can only occur in even number, but in large numbers it will still end up in an asymmetry. As an example, we can take 12 particles, 4 of each opposition, then 8 of them annihilate, and 4 of them stands out. Then they can annihilate completely, but they can also leave 2 particles of the same opposition, and that is what creates the asymmetry. Based on observations and calculations, around a billionth of the original particles did stand out and became the current universe, and that matches very well with this prediction. For the charge opposition inequality, there is not anymore an inequality. It is just that the third opposition does only appear for the color charge and not for the electrical charge, because both groups of antiparticles will annihilate identically and leave no traces of distinction between them. For the quantum field existence, I will just repeat what we have been through. The quarks are unified with the electrons, the generations are unified with each other accordingly, and again we unify the quarks with the electron, and what remains is just 3 oppositions of the same particle, the electron. We still have the neutrinos, which stands out here, but as far as we can unify all the charged particles and fundamental forces, everything indicates that everything hangs together in the same common field, and in some way the neutrinos must be excitations in the same field as the electrons. If we unify all the particles and fields into one, this is called a grand unification. The important thing to have in mind here is that the weak nuclear force was already unified with the electromagnetism in the 1960s with the electroweak theory, so it is only the strong nuclear force which stands out, and that is what we want to unify by building the quarks with equalized charges. Then we can go back to the periodic table, and as you might have noticed, the atom we have used for illustration has 6 electrons and 6 protons, which is a carbon atom, the atomic number 6. And as the protons are made of 3 oppositions of electrons, we can multiply the number of electrons it contains plus 1 electron with the atomic number, and then we get the total number of elementary charges that are confined within the different elements. For example, we can take carbon, which gets the number 108, iron 468, gold 1422, and so on. For neutrons, we can multiply with 22. Different elements can have different numbers of neutrons, so this does only apply to atomic isotopes. The important thing to have in mind here is that the periodic table is about chemistry, and we should ask us more often, why do different elements have different chemical properties in the first place? You might think that this is well defined by our current science, but I'm not that convinced. Electrons are not orbiting freely around the nucleus, they are waves and they are located in what is called the wave function. Erwin Schrödinger made an equation that works very well for that, although nobody knows why it works, it just works. And as a part of the wave function, the electrons are also partially within the nucleus and not as separated parts. Some kind of a vibrational dynamics must go on in the nucleus, and that is what steers the electrons, which would imply that chemistry has roots in and actually emerged from nuclear physics. It's just that our science has not came far enough for us to understand how. Then we can ask, how can the wave function have such fine shapes that are spatially fixed, and how can it have that big variation potential? And yeah, I think this supports the prediction that elementary particles are three-dimensional vibrations very well, otherwise the nucleus wouldn't have the leeway to enable so. And it's the same thing for spectroscopy and what we experience as light and radiation. Spectroscopy and chemistry are two aspects of the same thing, with the nuclear physics responsible for those phenomena to even exist. Lonely elementary particles do not have those properties, it's only as an atomic structure that they are able to absorb wavelengths at fixed values. Lonely particles are both waves and particles, known as the wave-particle duality. Although this is well understood from the double-slit experiment, it may also sound strange, but is it? If particles are vibrations in a field, the field will also dictate their propagation through the field, and in that sense there is no duality. Particles are particles, it's the field that makes them wave-like. We just don't have the knowledge about what that enables the field to work that way. Why empty space is not empty but full of energy, why time flows even in deep space between superclusters. A range of apparently different problems that probably hangs together. If we can unify the elementary particles, we can also get back on the same track that Einstein was on, and hunt for a unified field theory, where everything becomes unified with gravity. Gravity is caused by the slowing of time, and all constants have an aspect of time. It's the fundament for everything, and that's where we should be looking. In the seek after a complete understanding, it's important to remember that all our physical laws are built on constants. Elementary charges, elementary masses, the speed of light, the gravitational constant, the dielectric and magnetic constant, and so on. These are measured values, and it's completely unknown what they emerge from. It's a huge effort our historical scientists have done to figure out how all those constants hang together and can be formalized as physical laws. And that is something that has enabled our science to progress radically in the last centuries. But now it seems to be empty and there is no more constants to measure. Now we must go even deeper down to things. So do we need another approach to physics to do so? Well, let us put this in perspective. In our macroscopic world, we have all from orbiting planets to rotating engines and machines, which are all based on atoms, dominated by heat and temperature. Hereby we have two different frequency levels, which are all built on an even deeper frequency level, quantum physics, where we have nuclear physics and excitations of electrons. From level 1 to 2 we have fluid mechanics and, for example, also biology, which is further built on chemistry and thereby also directly connected to the third level. Then we can ask, are there any deeper frequency levels that all this is built on? A vibrational connection to something that generates all the physical constants? Well, let us introduce the father of some of the deepest physical constants of them all, Max Planck, the father of the Planck units. A Planck length is about 10 to the negative 25 meters, which means that it is smaller to the atomic nucleus than the atomic nucleus is to us. There is an equal distance down to the Planck length as there is up to 1 million times the observable universe of 93 billion light years across. So this is very, very deep, and it is the smallest length that we know of. You might think that nothing can be even smaller than that since it is as small, but this isn't necessarily the case, it is just a physical constant. We can also see the same thing in the aspect of time. The deepest time unit we so far have been able to measure is below an attosecond. We have never measured a septosecond or anything deeper than that. And as you can see, the distance down to the Planck time of 10 to the negative 43 seconds is long. But how can this constant exist in the first place? Does it imply that anything even deeper must exist for this constant to come about? Well, we don't know, and this is a question we should ask for all the constants we have. Something must be the fundament for the world we live in. Einstein once said something that might be even deeper than the Planck units. Everything is energy, and that's all there is to it. match the frequency of the reality you want, and you cannot help but get that reality. It can be no other way. This is not philosophy, this is physics. The inability to explain all the constants has led many physicists to seriously consider the idea that we could live in a simulation with the possible solution that all the constants are programmed into that simulation. Can it be that we live in a simulation? No, I don't think so, but that's just my opinion. I think there is an underlying physics that relates all the constants, and if we can unify everything to just one elementary charge, that makes things easier. And we can possibly rather use simulations to figure out how it hangs together. When we figure out to ask the right questions, there is a better chance that we find the right answers. Also with simulations. Certainly the simulations should know whether there exist many or just one field and elementary charge, in order to get on the right track. At the end we can ask why should we care about it. As an example, if we want to enable permanent biological life or just live some decades or centuries longer than we are evolved to, we need to develop new science and technologies. Just a few decades ago we believed that aging was caused by mutations to the DNA. Then we figured out that our DNA does not age. It's just how they're packaged around the histones and the DNA methylations that causes cells to lose their identity, and so we age. The atoms we are made of are built on energy conservation, and they do not age. They can live for billions and even trillions of years into the future. Then we can ask, when the atoms do not age, why should we? If we can develop an understanding of the atoms themselves, we can possibly develop technologies to live just as long as we want to. From an elementary perspective, there is nothing in physics that has to age. And that is just one of many reasons for why we should care more about nuclear physics. What is fundamental is not just a deep shadow, it's the building blocks of everything. In order to live longer, our population will also grow, so we need to find new ways to produce energy. And I'm pretty sure that the answer to that lies at the fundamental level as well. When we can convert matter into energy sustainably, we will, just like the sun, have virtually infinite energy supply for billions of years. If we could understand the underlying frequencies that enables the sun to fuse atoms at just 15 million degrees Celsius, which is about 10 times as cold as our current reactors aim for, we can turn net loss of energy into large net gain of energy with reactors that is just a fraction of the size of the current reactors, and that's where we should be. But can we do something even better? Yes, with antimatter there are even better opportunities. If we can produce antimatter through an artificial asymmetry generation, we can convert matter into pure energy, and that would even outcompete fusion and fission, which only releases a fraction of the atomic energy. Just 2 grams of matter can hold a Boeing 747 flying for an entire week, and that's the power of the energy that lies within everything. I have made a science paper about these topics, the new standard model and the periodic table. If you want to learn more about it, please follow the link in the description. At the end, I want to repeat what a wise man said already in the 17th century. Truth is ever to be found in simplicity, and not in multiplicity and confusion of things. Thanks for your attention. To send a signal to our nearest planetary system takes about 4 years. The next planetary systems are even more light years away. Most of them are thousands of light years away. But are any life out there? Well, our science has changed our viewpoint on that dramatically in the last decades. We now know that water is likely to be found everywhere around, not only in our own galaxy but also in the entire universe, as hydrogen and oxygen are among the most common elements out there. And so are carbon and the other elements that make up our biological life. They come from nuclear reactions in supernovas and are not unique to us. Several percent of all the planetary systems probably contain at least one planet in the habitable zone. And there are billions of billions of billions of them. And that is just in our very own galaxy, the Milky Way. Our supercluster may contain trillions of habitable planets, and it is just one of an unknown number of superclusters in the universe. Each supercluster contains hydrogen, oxygen and other elements, just like our own. But how large is the universe actually? Well, let us put this in perspective. Our solar system is home to 8 planets and 218 moons, and it is located in the interstellar neighborhood in the Milky Way galaxy, which contains 100 to 400 billion stars and 0.3 to 3 billion potential habitable planets. And the Milky Way is located in the local galactic group together with Andromeda and 50 other galaxies, which again is located in the local supercluster with about 10,000 galaxies. And we are again a part of Laniakea, which is home to about 100,000 galaxies. Laniakea is again located in the observable universe with 0.2 to 2 trillion galaxies. But what is the observable universe actually? The observable universe is how far matter and light has traveled since Big Bang, both away from us and to us, and that's why the observable universe is 93 billion light years across. Inside the observable universe we have internal structures that are several billion light years across, ranging to many percent of the observable diameter. Our own supercluster Laniakea is about 500 million light years across. Then you might wonder, what is outside the observable universe? Well, it's probably just more universe. How much is something we don't know. It can be 1,000 times bigger or even trillions of times bigger. But can we calculate the real size of the universe outside the observable? Yes, I think we can, and this is where I'm going to show you some techniques we can use to better understand how we can do so. If our observable universe is located in a concentration of matter that ends somewhere outside it, let us call it the cosmic galaxy. How large the universe is within that cosmic galaxy is something we don't know, and it can be placed anywhere within it. That cosmic galaxy is what came out of Big Bang. When the universe was born, it is estimated to have been reaching speeds that would equal to more than 1 trillion times the speed of light. This is called the inflation period of Big Bang. After that period, the universe was slowing down, but now it is again accelerating, and it seems to expand into nothing. But what is it that drives this expansion? This question is why astronomers believe that the universe consists of only 4 to 5% of normal matter. About 70% of the universe is thought to consist of dark energy, although nobody knows what dark energy is, and it is also debated whether it even exists. But can it be that we just overlook the big picture? Although 93 billion light years seems to be a very big size, it isn't necessarily the case at the cosmological scale. The universe can be even infinite, but the big question is, what kind of astronomical terrain are we located in? What kind of properties does it have? Let us visualize that Big Bang is situated in a field that is not expanding. When it inflates, it deforms the field around it, and thereby it creates a giant gravitational wave that is propagating into the deep space around it. The wavelength may be probably more than trillions of light years. How large, we don't know. Another place we have another Big Bang, and it does the same thing. As the wave propagates further, we come into wave crest, then we contract and implode back into a point again, just like where we came from before Big Bang. And then the same thing happens over and over again. You might think that the speed of light and thereby also the speed of gravitational influence prevents so, well, that's not the case. Many physicists have tried to solve physical problems by the distinction of the speed of light from gravity, but nobody has succeeded in doing so. We could be trapped within a gravitational wave, and it is because of that wave that the speed of light is what it is. They are true aspects of the same. There is, in fact, nothing to refute that we could actually live in such a cosmological wave complex. And based on the gravitational wave that was produced by Big Bang, we can also calculate how large the universe must be in order to absorb that wave as the least possible size of the universe. First, we calculate the least possible peak power of Big Bang, which is derived from the mass we know exists, and the estimated peak velocity of Big Bang. Then we use a reference for calculating the potential propagation length of the wave, which we again use as the radius to calculate the volume that must exist in order to absorb the energy of the wave. If we do this calculation, it turns out that our universe must be at least 10 to 174 cubic parsec, and that is 10 to 143 times bigger than our observable universe. How much of this volume that is filled with matter depends on the density of cosmic galaxies. Then you might wonder, with that many cosmic galaxies surrounding our observable universe that also existed before Big Bang, why don't we see any signs to them? First of all, it's important to have in mind that even to see a normal galaxy at the end of our observable universe is difficult, and the light from something more than trillions of light years away will be equivalently more redshifted. Additionally, all where we live came from Big Bang, so there is no light from something outside that has been able to reach us. Then we can ask, is the cosmological wave complex the largest that exists, or is there anything also outside of that? Most probably there is. It can be just a zone within an even larger wave complex, as a wave within a wave. And the actual universe can be, as far as we know, infinite. But if we are able to calculate the least possible size, this could be important to our viewpoint on cosmological questions. We can also see that in view of the fine-tuning problem, and that the constants in our universe seems to be fine-tuned for the existence of life. If there are almost endless numbers of cosmological wave complexes, there will also be a large number of different constants in the different zones, and that's why we and our part of the universe exists. I have made a science paper about these topics, dark energy and how we can calculate the size of the universe based on the gravitational wave produced by Big Bang. If you want to learn more about it, please follow the link in the description. No matter how large the universe is, just the very own galaxy that we live in is also huge, and high-resolution photos of all planets in our entire galaxy are flowing through our solar system every second. Planets with their unique landscape, unique mountains, unique oceans, and maybe also animals, forests and vegetation. You might wonder, well, with so many billions of planets out there, why don't we just place out a telescope, photograph those planets, and then we zoom into their surfaces to see what is going on there? Well, it's not that easy. Our telescopes are not just small from an outside view, they are rather microscopic. It's hard to receive just a few photons from a single planet light years away with telescopes that small. So what should we do? Are we lost forever? Not necessarily. There are opportunities. Among them is the Sun itself. The Sun works like a gravitational lens. It bends light. The problem is just that the focal point of the Sun is 550 times further away from it than we are. That equals to 76 light hours. And this is where we should place out our telescope. Then we receive what is known as an Einstein ring. Although the Sun itself blocks most of the light, it will equal to a telescope with a diameter of 75,000 kilometers, while our telescopes in space today are just a few meters. This is known as a cosmic telescope. In the future, it is possible that we can build a satellite system around our Sun at this orbital distance. Then we can photograph millions of planets in many different angles at once. However, this concept do also have limitations, and it is hard to scale up further. The Sun is the size that it is. Can we, for example, zoom in even small animals thousands of light years away? No, this will still be pretty impossible. So can we do something even better? Yes, I think we can, and we can do something much better. If we succeed in building more powerful lasers, we may be able to produce Kugelblitzes, microscopic black holes, that are sent into a collision center at very high speeds, and then we generate sharp gravitational waves that, depending on the waveform, will bend light in certain angles. Then we can place out such a generator in space and flash a disk of light into a focal point. The size of the disk does only depend on the power of the generator, so this principle has scalable potential. If the generator is powerful enough, it can act as a telescope with diameter of millions of kilometers and all the way up to several light minutes and larger. But most importantly, it is the flexibility of this principle. We can place it out anywhere in space and freely change the direction of it. That would enable us to collect high-resolution photos of all the planets in the Milky Way and zoom into them like a Google Earth. With future technology, we may also be able to convert them into 3D and navigate around on those planets in a VR mode. And there might be an even larger number of moons. For all we know, are moons more commonly inhabited than planets. If a gas giant first orbits in the habitable zone, it can be home to tens of habitable moons in the same planetary system. The opportunities are many, just waiting for us to discover them. The big question is then, how far into the future are we talking about? Well, technological development is first of all resource demanding. It takes time, only because the resources usually are not where they should be. Although our galaxy contains large numbers of planetary systems, we have so far barely reached out of our own solar system. Our space travel does not reach very far, and neither do our signals. Based on the speed of light, it takes hundreds of years just to send a signal out of a tiny zone within our galaxy. But let's say there is a planet 100 light years away that is hosting intelligent life and a community that we want to reach out to. How can we connect with them? Based on our current technology, it takes 100 years just to send a signal one way. If we send a signal today, it will not reach that planet before the 22nd century. And that is what we need to do something with. Our reach in space is first of all determined by the aspect of time. If we double the distance of how far we can reach out, from 50 to 100 light years, we can reach a volume of planets that is 8 times bigger. If we double again, we can reach 64 times bigger. And double again, we can reach 512 times bigger, and so on. It increases exponentially with our reach. How many planets that are within that volume depends on the distribution within our galaxy. We live in a spiral arm, and the galaxy is about 1000 light years high in the vertical direction. The density of stars increases towards its center. In intergalactic conditions, the volume would increase 1 billion times for each time we increase the reach just 1000 times. So the thing is that we are, from an outside view, trapped within not just a small but rather microscopic volume of the universe. And the volume outside it is, as far as we know, endless. But how can we do something with it? Many people use Einstein as a reference for that nothing can travel faster than the speed of light. But did he believe so? Well, Einstein was one of the first persons to suggest how we can change the speed of light, known as an Einstein-Rosen bridge. The thing is that changing the speed of light is not a superluminal speed, it's the light itself that changes velocity. And it does not need to break causality either. Relativity is classical theory, and we don't have theory to define causality conditions elementary. It is, however, debated whether a wormhole is possible, and if it should be, there are many practical problems as well that makes it virtually impossible to use for communication. Although it may create a direct connection, it takes long time just to enter the wormhole, and besides it requires large amounts of energy to create it. But do we really need a black hole in order to change the speed of light? Let us look more into that. The highest energy concentration we so far has been able to reach with our best optics, most powerful lasers and deepest pulses is at the zeta-watt level, measured by watts per square centimeter. We have so far never been able to reach a yottawatt or anything higher. You might think that if we go too high we just create a microscopic black hole, but that depends on how deep we pulse it. In order to make a black hole we need to exceed what is called the Planck energy of 2.2 gigajoules. As far as we keep it below that, we don't create a black hole. We use just 1 joule of energy if we concentrate it enough and then pulse it to 10 to the negative 30 seconds. Then we reach an energy density of 10 to 40 watts per square centimeter, which is 1 million trillion times higher than we so far has been able to reach. The big question is then, can space take up infinitely high energy densities without changing properties? The thing is that we don't know the energy density of the vacuum itself, a problem called the vacuum catastrophe. It is not unlikely that the speed of light must change when we surpass a certain level. The levels we have reached so far is small compared to what is principally possible through deep pulsating. Yet the speed of light is just a measured constant, and we do not know why it is what it is. Then we can ask, what would happen if we change the speed of light? In order for velocity change to happen, it must have a direction. When the speed of light changes, we get what is called self-focusing, and the light concentrates towards the center. When it becomes concentrated enough, the core starts to defocus, so it balances each other out. Then the velocity change propagates as a filament through space, and this is known as filamentation. We know that because we have discovered many different types of self-focusing phenomena, and when a filamentation occurs, it can propagate kilometers through our atmosphere, and as far as we know, without an end, if the filament didn't lose energy through the air. If we can make such a filamentation by changing the properties of the field itself, we can call this a quantum filamentation. That means that we create a connection between two coordinates with its own internal speed conditions, which we can control with the intensity. We can call this a vectorless connection because it does not obey the vector rules of the surrounding field. The big benefit it has compared to an Einstein-Rosen bridge is that we can generate this connection just with a deep laser pulse and no larger lasers than we already have built. This way we can make many such filaments in different directions simultaneously, just from a simple satellite or space station. It also connects the coordinates directly, so it does not take time to enter it. If we increase the speed of light 1 billion times, we can reach a distance of 31 light years within a second. If we increase it a trillion times, we can reach 31,000 light years in a second, and that's where we should be. At that distance, there would be billions of planets within reach. We could reach near half of the entire galaxy. If this is possible, it is not unlikely that there already exist networks of digital connections between civilizations, maybe also in our own galaxy. That depends on how many civilizations we have, which certainly varies from galaxy to galaxy. Some civilizations may share just internet and TV where they can trade news, movies, music and whatever a digital connection opens for, while other civilizations may also exchange business cooperations and intellectual properties like patents and digital files for gene modification and 3D printing of new technologies, and whatever might be enabled by our future industry. And as we can regulate the speed conditions through quantum filamentation, it also has a scalable potential. If distant galaxies are reachable within seconds, it is not unlikely that there already exists an intergalactic society, maybe also in our own galactic group. Our neighbor galaxy, Andromeda, contains around 1 trillion stars, 3 to 5 times bigger than the Milky Way. So if there were 100 civilizations in the Milky Way, there might be 400 civilizations in Andromeda. And it would be a great milestone to reach out to someone there who might be even more advanced and have connections further to other galactic groups. Our supercluster Laniakea contains about 100,000 galaxies, and if there is a cooperation and trade interest between galaxies within it, it might be possible that some of them are so advanced that they also connect the intergalactic society to other superclusters. Then we have hundreds of billions of galaxies just in our observable universe. And the superclusters located at our cosmological horizon may also have future connections outside of that too. And maybe also to other cosmic galaxies. Well, that will just be pure speculations, but what do we know? Why should anyone contact us? Our galaxy has been habitable for billions of years, even before the sun was born. And we have been industrialized just for a few centuries. And who should they contact? The White House in the United States? Or maybe China. It might be that they rather protect us just like we protect our aborigines in rainforests, and let the development move on undisturbed until we reach them by ourselves. It might be that we just don't understand enough to be included in an intergalactic society. All our technology is just built on matter, while the energy itself that builds the matter does not have a technological function. All our science is matter-based, and we do not understand the energy itself. We are what we can call a matter technological civilization. Will we ever become an energy technological civilization? A civilization that understands the energy in itself? Maybe. So far we have been through 3 industrial revolutions, and a 4th industrial revolution is going on. Will it be one of the next revolutions that will enable us to colonize other planetary systems? It might be. But if so, we should be aware that there might already exist an intergalactic society that observe what we are doing. The galaxies are there, and the superclusters are there, filled with trillions of planetary systems containing hydrogen, oxygen, water and all the elements that come out from supernovas, ready to evolve biological life that will develop technology and reach out to each other. That could be what we one day will meet. An intergalactic society dominated by rules, trade interests, energy administration and management, local rules and alliances, and at the bottom of the triangle there might be a large number of protected habitats and primitive civilizations under development, and we might be one of them. Just a few decades ago, some people were almost laughing when someone believed in the existence of other civilizations. Today, nobody can, based on knowledge we have, refute that the probability for numerous other civilizations to exist is high, and astrobiologists has taken this research to a new level. But what about an intergalactic society? Should we just laugh about that too, or should we take it seriously and research which types of society that can be a real possibility? Whether such a community can exist or not all depends on the speed conditions for communication. No communication, no community. Yet we have to settle for that the unknown unknowns are many, and might open for such a community to actually exist. But what should we be afraid for? Like our international community stabilized Earth, might be just how an intergalactic society stabilized the universe and the energy administration of galaxies, and why we never see any signs to the existence of anyone. They are preoccupied by intergalactic trade interests and politics, and don't worry the same way about protected habitats like us. If just 1 in a million of all the planets are home to a civilization, there will for each human being on Earth exist millions of civilizations, just in the observable universe. If we should have a phone reporter for each of those worlds, we would need to increase our population from billions to quadrillions, and still will there exist one undiscovered world for each person. The problem with intergalactic communication is not the emptiness of large distances, it's all the invisible energy that makes time flow within that space. Empty space is not empty, it's full of energy, giving the space properties. As we don't understand how, neither can we identify its energy density. The vacuum catastrophe is both a physical and cosmological problem. As Einstein said, time is what we measure with a clock. What he didn't say but might have thought is that the space that drives this clock may have roots in frequencies so deep that our society is not even ready to hear about it. No fundamental physical laws are actually fundamental, only nature itself can be, and it's found in the constants themselves, not just the number. That's a truth that will make all of science. If you want to learn more about quantum filamentation, I have wrote a book about this and other topics, how it can change our society from a scientific viewpoint, also in connection with my hypothesis for unified field theory, and the same for telescopic solutions, wireless energy transfer, rocket technology and space travel, antimatter and nuclear fusion, and many other topics. It is named the upcoming industrial revolutions. Currently only written in my own language, Norwegian, but will hopefully be translated to other language in the years to come.